All right, we're ready to take a look here at number 2. All right, in the 1980s, it was believed that congenital abnormalities affected about 5.2% of the nation's children. Some people believe that the increase in the number of chemicals in the environment has also led to an increase in the incidence of abnormalities. A recent study examined 384 children and found that 28 of them showed signs of abnormality. Using a 1% significance level, test the claim. So there's our claim. Test the claim that the percentage of children affected by congenital abnormalities is higher than it was in the 1980s. So that was 5.2%. Okay, hypotheses. All right, so the claim is that population proportion of all children affected by congenital abnormalities is higher, so is greater than 5.2%, and that's 0.052. So greater than is our right tail test. Null hypothesis is equality, with that same value, 0.052, that was in the claim. Right, we have our p0, 0.052, and that will be the center of our graph, 0.052. And then they're going to go out and get some data to see if there's evidence that the proportion is greater. So they did a study of sample size N, 384 children, and of those, X, the number that showed signs of abnormality, 28. Alpha, we're using a 1% significance level, 0.01. All right, so we'll run our one proportion z-test. So back to our tests, one proportion z. And put in our p0, our x, and n. And our direction of our test is now a right tail test. So we want p greater than our p0 value. And then calculate. All right, I can see my p hat there. I will just do 2 decimal places just to record that and get our visual going. So p hat, 0.07. So as a percent, that would be 7%. So in the 1980s, it was 5.2%, and 7% is higher. The question is it high enough to really convince me that the 5.2% is the incorrect population proportion? So to determine where 7% is on this graph, we graph its corresponding test value, and that z-score to 2 decimal places there is 1.85. And then we'll be able to graph that and draw some conclusions. All right, so I'm going to set up again my traditional method first. It's a right tail test. So the area to the right of the critical value is going to be alpha, in this case 0.01. And we want to find that critical value using inverse norm. We need the area left of it. So 1 minus our alpha, and that will be 0.99. So that critical value will inverse norm, 0.99. And that is 2.33. And it's positive, that makes sense because it's a right tail test. The critical value should be on the right. So critical value 2.33. And that was established based on the chosen significance level alpha. So that area is our alpha, 1%. And the z-scores in that region make up your critical region. Unshaded represents our non-critical region. Okay, there's the setup for a traditional method. And then we're ready to see where our test value is located. So it's z-score, the z-score for the test value, 1.85. So that would be around there. So that tells me that that p hat, 0.07, is to the right of 0.52, but it has not made it into the critical region. It's in that unshaded non-critical region. So my test value falls in the non-critical region, which means we do not reject the null hypothesis. So it's just not far enough to the right to really convince us to reject that the proportion is 5.2%. So let's write the decision here. So anytime your test value falls in the non-critical region, your decision is do not reject H naught. And that means that even before I draw a picture or look at a p-value, because of the relationship between the methods, anytime my test value is not in the critical region, so I don't reject the null hypothesis, that guarantees that your p-value had to be bigger than your alpha. So those always go together. Test value not critical is going to give me a big p-value. So let's graph it and see if that looks true visually first. So here's 0.052. And then the test value, 1.85, told me that my p hat is there. And in a right tail test, the p-value is the area to the right of the test value. So now I can see visually that that p-value area is bigger than the alpha area. So up top here, the p-value would be everything from 0.07 over all of that. So that area is bigger than the alpha area. So that makes sense visually. And then we'll go ahead and confirm it numerically by bringing up the test again. And let me just run the test and write down that p-value, 0.0324. Zero, oops, 0.0324 for 3.24%. So 3.24% indeed is bigger than our alpha, which was just 1%. So my p-value, 3.24%, is bigger than my alpha, which was just 1%. Okay, so either method, you come to the same decision, and then our conclusion, if you don't reject the null, that means you don't support your claim. So using a 1% significance level, do not reject the null, so there's not enough evidence to support the claim that the percentage of children affected by congenital abnormalities is greater than 5.2%. Okay. So there's another Great, Tim.